Hello everyone. Today, I will present our work on enhancing signal processing with multi-layer perceptron utilization for bit pattern magnetic recording. This research is a collaboration between King Mongkut's Institute of Technology Lakrabang and Tohoku University. By 2025, the world will be generating an enormous amount of data. This growth is driven by the Internet of Things, cloud services, and AI applications. As data demand rises, storage systems must evolve to keep pace. Current hard disk technology is limited by the superparamagnetic effect. At very small grain sizes, thermal instabilities reduce magnetic stability. As a result, conventional media can only reach about 1.0 terabit per square inch. This becomes a bottleneck for future storage needs. To overcome this limit, several new technologies have been proposed. Among these, bit pattern magnetic recording is especially attractive due to its ability to achieve much higher areal density without thermal stability issues. In bit pattern magnetic recording, each bit is stored in a pre-patterned magnetic island. This eliminates random grain noise and improves thermal stability. Compared with conventional granular media, BPMR can increase the areal density up to 4 to 5 terabits per square inch. Therefore, BPMR is a promising candidate for next-generation hard disk drives. Here, we propose two channel models for bit pattern magnetic recording systems. System 1 uses an MLP-based equalizer followed by a conventional SOVA detector and LDPC decoder. The equalizer's role is to reduce inter-symbol and inter-track interference before the detection stage, improving the reliability of the recovered bits. System 2 goes one step further by replacing both the equalizer and detector with an MLP-based detector. This model directly maps the noisy readback signal to estimated bits, which are then decoded by the LDPC decoder. In our study, we consider a recording density of 4.0 terabits per square inch. On the left, you can see the cross-sectional structure of the BPMR media, which consists of a 300 nanometers soft underlayer, a 15 nanometers interlayer, a 10 nanometers recording layer, and a 5 nanometers head media spacing. On the right, two types of bit island arrangements are used, A, regular, and B, staggered. Both have a bit length and track pitch of 13 nanometers and a bit diameter of 10 nanometers. The staggered arrangement helps reduce inter-track interference compared to the regular case. Now let's take a closer look at System 1, which is the proposed MLP-based equalizer model. The process works in two main steps. First step, we prepare the input and output for the MLP equalizer by applying the MMSE and LMS algorithms. This helps generate the target coefficients and desired signals for training. Second step, we train the MLP-based equalizer itself, where the received noisy signals are mapped to the desired signals through multiple hidden layers. Next, we move to System 2, which is the proposed MLP-based detector. Unlike System I, this model removes the equalizer and SOVA detector and instead uses the MLP directly as a detector. The received noisy signal is fed into the MLP model, which learns to map it directly to the recorded bits. The detector produces log likelihood ratios, LLRs, through the LLR calculator, and these soft decisions are then passed to the LDPC decoder for error correction. It shows that the proposed MLP-based equalizer consistently achieves lower mean squared error, MSE, values across all signal-to-noise ratio, SNR, levels compared with the conventional 1D MMSE equalizer in both regular and staggered BPMR media. This demonstrates that the MLP equalizer more effectively mitigates nonlinear ISI and ITI, resulting in superior equalization performance. The performance shows that the proposed MLP-based detector achieves the best BER performance across all SNR levels compared with both 1D and 2D PRML systems, with staggered bit island arrangements consistently outperforming regular ones due to reduced ITI. At a BER of about 1.0, the MLP-based detector provides gains of roughly 0.5 dB for staggered and 1.2 dB for regular media over the MLP-based equalizer. Thank you for your listen.